as long as the two vectors have the same number of entries, we can compute the dot product. So it works in R2, it works in R3, it works in R4 as long as the vectors are the same length. So if we have these two vectors, u equals the vector 2, 3, and v is the vector 1, negative 5, we can still calculate their dot product. So u dot v would mean to take u transpose, which is 2, 3, times v, which remember the comma means over, so that's 1, negative 5. We get 2 times 1 is 2, 3 times negative 5 is negative 15, so 2 minus 15 is negative 13 for the dot product. Or if we had some other vectors, maybe we've got this vector w that has 4 entries, 1, 0, negative 5, and 7, and another vector z that has also 4 entries, 2, 1, 3, 5, then we could find their dot product, w dot z. We're just multiplying corresponding entries and adding them up, right? No need to write out the matrix definition. I just wanted you to see that that's related. So we have 1 times 2 plus 0 times 1 minus 5 times 3 plus 7 times 5. So we have 2 minus 15 plus 35. Let's see, negative 15 and 35 would be 20, plus 2 makes 22 for that dot product. So as long as the two vectors have the same number of entries, you can compute the dot product. Of course, we couldn't do u dotted with w or v dotted with w or some combination like that because the number of entries don't match, just like you can't multiply two matrices unless the number of columns of the first matches the number of rows of the second. So our next question is, what does the dot product mean? So it has a few uses, and our first thing to notice is that the dot product does something about measuring the length of a vector. So imagine we have a vector u, and u is 1, 2, 3 here. Now remember, how you would find the length of u is to take the square root of the sum of the squares of the individual entries. So we'd get the square root of 9 plus 4 plus 1, that's the square root of 14, that's the length of u. Notice what we get if we do u dotted with u. If you take a vector and you dot it with itself, then when you multiply the corresponding entries, you're actually squaring the individual entries of the vector. So when you take u dot u, you're actually computing not the length, but almost the length. You're computing the length squared, right? So the only thing you're missing when you dot a vector with itself is taking the square root. So dotting a vector with itself measures the length. Here's another cool thing about the dot product. If you have the dot product of the sum of two vectors, parentheses, it actually equals u dot v plus u dot w. We could do this in a simple case. So so if we just do it in the case of R2, u would have entries u1, u2, and v would have to have two entries. We'll call them v1 and v2, and w would have to have two entries. Let's call them w1 and w2. And let's check both sides of this. U dotted with v plus w, let's see, that would be the vector u, which is u1, u2, dotted with, if you take v plus w, remember to add two vectors, you just add their corresponding entries, so v1 plus w1, v2 plus w2. And so now we do the dot product, we end up with u1 times v1 plus w1, that would be u1 v1 plus u1 w1 plus, we take multiply the second entries, so u2 times v2 plus w2 would be u2 v2 plus u2 w2. And if we separate those out, then we have u1 v1 plus u2 v2, and we have u1 w1 plus u2 w2. And so all we've done is just rearrange the order of addition here. And notice that is u dot v plus u dot w. That means when you go to multiply, say, we have the distributive property here, so if I were to take u plus v and multiply by w plus z, if I do the dot product, I need a dot in the middle there, then this is going to work just like when we multiply two binomials, because the FOIL method works because of the distributive property. So if we do this, we know we're going to get u dotted with w and u dotted with z and v dotted with w and v dotted with z. So it's because of the distributive property that we have this FOIL method. We can take the dot of the first, the dot of the outsides, the dot of the insides, and the dot of the last. So that property still works with the dot product, even though we're multiplying vectors and not just multiplying single numbers.